right, so welcome everyone. I think we can get started. So today's speaker is Lorenzo Davoli. Lorenzo graduated from Physics of Complex System, and he is now a PhD candidate in the group of Ocean, Atmosphere, and Climate Dynamics at the University of Milano-Bicocca in Italy. And today, Lorenzo will tell us a bit about the work he has done on the role of the atmospheric state in the modulation of the SST wind coupling. So you see the title of his presentation here. And I think that with this, Lorenzo, the floor is yours and you can start.
Okay. Thank you, Agostino, for the introduction. Thank you, everybody, for having me here and attending this presentation. I'm really glad I had the opportunity to share our most recent work with you today because I think it fits nicely with the content of the last seminar in this mini-series about the momentum transport within the marine atmospheric boundary layer. So during last seminar the last week, we had Luis Nuyens, who was telling us about how clouds play an extremely relevant role in transferring momentum through the marine boundary layer all the way down to the surface, especially in the tropical area. And today's presentation is going to unravel a bit a different mechanism that plays a similar role, but on a global level, also in other regions. So while Luis was focusing on mostly on tropical areas where the sea surface temperature gradients are quite shallow, as she was saying, she loves to call it the warm pond, I believe. These in the warm soup. In this case, in situation where the SST gradients are more relevant, we have a feedback of the atmosphere or the marine boundary layer that can be observed on the surface wind. And we are going to do that by employing, we have been doing that employing satellite data and reanalysis. And for this reason, the scales of our study are a bit different from the one presented last week. So we're talking about here about the mesoscales, so tens to thousands of kilometers. And I would like to start exactly by looking at the scales. So to answer the question, what are the sea surface temperature scales that actually matter, that have an imprint on the atmosphere? And what I'm showing you here on the left is a sort of homebrew product of sea surface temperature obtained from an L4 ESA CCI SST product, which has been overlapped with the Sentinel-3 estimates of SST at the kilometer scales. And as you can see, there's reach of very fine SST structures. And we are looking here at the Gulf Stream in its northern part during the summer season, if I'm not wrong. And we have a very relevant temperature gradient in the order of 15 degrees per tenth of kilometers. And I would like to compare this with the variability that we actually observe from SAR data, so from sea surface roughness data. And these observations are thought to be a representation of the imprint of the atmosphere onto the sea surface. And as we can see, both these large-scale meanderings are matched by the sea surface, by the Mabel dynamics, but also these very small SST features here, these little eddies, are indeed have a correspondence into the boundary layer activity. So now I would like to investigate one specific mechanism during this talk, which is the downward mixing. And I believe most of you are familiar with it, but I will go through it very briefly. This mechanism is observed whenever we have air masses crossing a sea surface temperature gradient. And in particular, in the case when we go from a cold ocean to a warm patch, what we observe is an increase of surface wind speed, fine-scale surface wind speed. And this is due to the fact that by going over a warmer part of the ocean, we increase heat surface turbulent fluxes. And that also has an effect on mixing and therefore on the boundary layer high. That causes entrainment of air masses which have higher momentum because we entrain the geostrophic wind from above the boundary layer. And this momentum is mixed all the way down to the surface, causing this fine scale increase. Now, in a condition where this is the only mechanism generating fine scale wind variability at the surface, we would observe something like this. So we would have a positive correlation between the sea surface temperature gradient and the surface wind speed. However, that's most of the time not the case. And so to identify what is the intensity of this coupling and what is the contribution of the SST to the fine scale wind response, in our work, we employed a matrix developed by Agostino, 2023, where we use as a natural frame of reference, the one oriented along the large-scale geostrophic wind direction. And so we take the gradients of the SST and the gradients of the fine-scale wind along this direction, and by computing a linear regression, we estimate the slope and we take this as an indication of how intense the coupling is. Now, this is a representation of the two fields that I just presented to you that we obtained from the Worf-Croco numerical simulations. What you can notice at first glance is that there are very different timescales variability in the two products. Here on the left, you have the sea surface temperature gradients, and on the right, you have the fine scale wind variability. And the atmosphere, as also Luis was saying last week, is doing a lot of dynamics by itself that clearly doesn't follow the timescales of the SST. But it's really interesting to notice that even with all this variability, there are some features you can see here and here, which are persistent, and they are linked to the fine scale variability of the ocean. So these are the response of the atmosphere to this SST patterns. However, this doesn't happen in all the possible conditions. For instance, here, what you are observing on the right is the presence of a cold air outbreak that is blowing from the continent, is blowing cold air from the continent over the warmer sea surface. And in this condition, we can notice that even the few traces of this SST wind coupling that we could observe here and here, and also there is a little bit of a hint here over here. Well, they disappear after the cold air outbreak has struck. And that seems to suggest that there are environmental conditions where this coupling is not active. And indeed, there has been some relevant work that has been done to investigate this phenomenon. The most relevant for this work is the one by De Bioleta in 2023, but similar results were also obtained by Niklas Schneider in 2020. And regarding the study of 2023, this has been carried out by using Reanalysis data. So these are AirFi, these are the results. And the authors were looking into the influence of the large-scale background wind speed and the air-sea temperature difference, which is a proxy for atmospheric instability in this case, to investigate how the coupling was affected. Now, clearly, we expect some differences between reanalysis data and observational data. For instance, we have quite different scales in terms of the SST field, but also there are some biases, known biases in R5. So what our research questions were based on this, on the fact that we are not sure if this behavior that was identified in R5 data is actually matched by the observations. And so we wanted to look into that. But also these analyses that I'm showing here are related to a global domain. And we know there are relevant regional features that can affect these results. And so we want to also to investigate what is happening at the regional scale and if R5 is able to properly represent the regional features. So this is a brief overview of the data that we have employed. We have carried out both global and regional analysis. The regions are shown in the map over here. And what you can see is that we have a 4/5 mid-latitudes region, mostly western boundary conditions due to the rich SST temperature patterns. And we also have some tropical areas, the Eureka region, so tropical Atlantic, and an Ibus region near the Pinguila Current, so an upwelling region. In terms of the dataset that we are using, we have employed metopay estimates of wind from a scatterometer and a radiometer SST measures, and the RFF data as a comparison. And unfortunately, for what regard the atmospheric instability, there is currently no satellite product that allow us to estimate fluxes or the air temperature in order to have an observational estimate of this of the atmospheric instability, and so we had to rely on Air5 for that. Hopefully, this is going to change with the advent of Harmony and with some new products that have been currently under development, but for now they are not yet available. So let's jump into some of the results. This graph is representing the behavior of the coupling coefficient as a function of the large-scale wind speed. And the solid line is the one related to the observational study, while the dashed line is related to the ERA5 counterpart. And what I would like you to notice here is that they share some common behavior. So we have an initial increase with increasing wind speeds, which is reasonable because we expect a higher availability of momentum given a higher wind speed in the free tropospheric wind, in the geostrophic wind. But then this increase is followed by a peak and then followed by a decrease. And in our interpretation of the Piavetal in 2023, the presence of this coupling is related to a balance between the advected timescale and the response timescale. In fact, we can imagine that as an air parcel is being advected over the SST gradients, there is an adjustment time that the air parcel needs in order to exchange heat with the underlying SST field. And with increasing wind speeds, we know the advected time decreases because as I formulated here, we can expect the advected time to be in the order of the size of the SST characteristic length scale divided by the velocity of the wind that is blowing the air parcel away from the SST gradient. And so clearly for increasing wind speeds, we are going to have shorter and shorter advected timescale. At a certain point, the atmosphere just doesn't have the time to adjust, and therefore the coupling vanishes. So it's also worth looking a bit more in detail into this reasoning because this is quite qualitative. And so what we thought of doing is we try to simulate a modification in the characteristic length scale of these SST gradients. And we did so by smoothing one of the regional analyses carried out over the Gulf Stream. And this is what I'm showing you here. So we have still the behavior of the coupling coefficient with respect to the large-scale wind speed. And we have the original curve that we observe over the Gulf Stream in green. And the two smoothings, the first one is in orange and is for a 15 kilometers Gaussian smoothing. And the second one in red is obtained for 25 kilometers smoothing. And I shall remind you that the original resolution is 5 kilometers for the SST field. And indeed, what we observe is that by smoothing the products, and so by increasing LSST, the characteristic length scale, we indeed move the peak forward to higher and higher wind speed because the SST feature become larger, and so it takes more time to advect them, and so the coupling remains relevant for a longer time. So we have established the difference. We can look into, we can interpret the difference between the AR5 result and the meetup under this lens. And I would like now to focus on the other graph, the graph on the left that represents the behavior of the coupling with respect to atmospheric stability. So what I represented here with the shades, violet shades, is approximately the neutral conditions, while on the left you have unstable condition and on the right you have stable one. And what we can appreciate is that the two curves share similar behavior for what regards the position of the peak, in the sense that we have the coupling peaks for conditions which are marginally unstable to neutral to marginally stable. And this is reasonable because we can expect the mixing induced by the SST gradients to be relevant only in those conditions where there are not either stronger mixing already at play, like what happened for strongly unstable conditions, or whenever the atmosphere is not strongly stratified, because in these conditions, the perturbation induced by the SST gradients can be not enough to perturbate the wall column. However, the two products have quite a starking difference, which is their behavior for marginally stable, and marginally unstable conditions. And I would like to interpret this in terms of the asymmetry with respect to the marginally unstable conditions, which I think is the most relevant thing to look at. And what we believe is happening here is that AR5 has known biases in the representation of stable boundary layer in terms of the depth of the set boundary layer. And in fact, we would expect the intensity of the atmospheric response to be dependent on the amount of air that the perturbation, the mixing, the perturbation induced by the SST forcing has to mix. And clearly, in stable condition, we expect shallower boundary layers compared to the unstable conditions. And so we expect to have a stronger wind response and therefore a stronger coupling. But this behavior, while it's matched by the observations, is definitely not matched by AR5 data. And we do not have a way to investigate this hypothesis using observations, because there are not observations. We don't have observations of boundary layer high with appropriate coverage of resolution. And so we had to employ some high resolution coupled numerical models, Worf-Krockow in this case, in order to try to prove this reasoning. And indeed, what we found is that for increasing high wind speed, for increasingly thick boundary layer height, here in the abscissa, we have increasingly weaker coupling, which is consistent with our hypothesis. However, what is unexpected is the fact that for boundary layer height smaller than 200 meters, we have actually quite a sharp decrease in the coupling intensity. And we believe, but this is a preliminary result, that this is due to the fact that these very thin boundary layers occur in quite specific conditions, maybe in conditions of weak wind or in very strongly stratified boundary layers. And as we saw earlier, both these conditions are conditions where the coupling is not really strong. So we believe this is the reason for this behavior that we observe from the Worf-Krockow model. Now, to summarize, we have added quite a few elements to our previous interpretation of the downward momentum mixing mechanism. We have seen that in terms of the enhancing the atmospheric response on the surface wind, the intensity of the SST gradient isn't the only relevant element, but also the size of the SST features plays a role in the way that it influences the advective timescale and the balance of these scales with the response timescale. But also there is a relevant role of the boundary layer height, which is linked to the amount of air to be mixed by this by the SST forcing. Now, what we would like to do was to give a mathematical framework to our hypothesis. To this aim, we developed some quite simple model describing the scaling of the wind, fine-scale wind variability with a large-scale wind speed. And the goal of this model is just to describe, not to define what this fine-scale wind variability induced by the downward to mixing is, but to describe how its intensity varies by increasing, if we increase only the large-scale geostrophic wind, so the source of our momentum here. And this is the analytical form that we have employed. And as you can see, it's composed by two factors. The first one is just a linear scaling of the SST anomaly, of the surface wind anomaly with the geostrophic wind speed. And this is the coefficient here is just a fraction, because we expect just a fraction of the momentum to be mixed all the way down to the surface. While the second term is what describes the decoupling of the decoupling of the SST of the atmosphere from the SST due to the advective timescales balance with respect to the response timescale. So we already said what a rough estimate of the advective timescale is, but now we need also to define what a reasonable scaling for the response timescale would be. And we, from the literature, what we found is that we can expect a linear, or in certain cases, power law dependence of this response timescale with the boundary layer height h. And still, from the literature, we found that we can find that the scaling of the boundary layer height is, in most of the cases, follows a power law with respect to the geostrophic wind. And we leave this as a free parameters because depending on the condition, depending on the references, this value can change quite a bit. But employing these definitions and within this assumption, we can find an estimate for the coupling coefficient, which is the one I reported here. So you still see the contribution, the linear contribution of the geostrophic wind, and here the decay due to the balance between advective and response timescale that here I explicitly reported, where C is basically containing all the constants that do not depend on the wind speed. And this term is indeed a decaying term because from the literature we expect this new exponent to be larger than 1, and therefore this term vanishes for increasingly strong large-scale geostrophic winds. So this is our empirical model, and we clearly we have to fit it to our observation to evaluate whether it's working or not. And we do expect it the model to fit the observation quite well, since we define the model to have this shape. So what we want to look at now is whether the parameters that we have estimated through the fitting are actually realistic. And there are three main free parameters, which are this gamma prime, C LSST, where LSST is the large-scale SST feature characteristic length, the characteristic length of the SST features, and the nu, so the exponent here. Fortunately, we do have from the literature an idea of how the boundary layer should scale with the geostrophic wind, and therefore we could compare our result with the literature, and we obtain from the literature that we expect a value of nu of 3 in the case of stable conditions, which is quite well matched in our case, and a value of 1.5 for unstable condition, and we slightly overestimated. But what is important, we believe, is that still we maintain the fact that for stable condition we have a higher exponent than for unstable ones. And so we are perfectly within the range of the expected values. And unfortunately, we do not have a physical counterpart to verify the values of gamma prime and the CLSST term. However, what we do know is that we could there is a variability on the sorry. There is a variability on the scale of the SST features in terms of the latitude, because this characteristic length scale is supposed to scale has the Rossby radius of deformation. And so what we wanted to do is to fit LSST to obtain an estimate of LSST from fitting our different regions, and in particular regions at different latitudes. But unfortunately, we do not have enough point to do so because the two tropical regions that we have considered. But if you remember, when we first introduced the characteristic length scale of the SST features, that was because we were noticing, because we were defining how the coupling was scaling, the position of the peak of the coupling with respect to large-scale wind speed was varying. And so what we thought of doing was to obtain the equation for the position of the peak from our analytical definition of the coupling coefficient, and then invert this equation in order to obtain an estimate of LSST from the position of the peak, that indeed, both in the mid-latitudes, but also in this case, in the Benguela current, we can estimate. And that's what I'm reporting here in the graph. So this is here in solid, you have the function definition of U peak, analytical definition of U peak as a function of CLSST following our model. And we have estimated the value of U peak from our regional analysis. So for the Gulf Stream, for instance, we have a value of approximately 7. For the Benguela current, approximately 11. And following the analytical expression for U, we can estimate what the expected CLSST for these two regions is. And by taking the ratio, we found a value of 0.39, which is comparable with the ratio of the Rossby radius of deformation in the two regions. And so we think our model gets this scaling quite right. Very briefly, I would like to show you what are a couple of features of the regional results. The first thing that I would like you to notice is I'm reporting here very, very small, but just as a reminder, what the global trend were. And as you can see, they are quite closely matched by the mid-latitudes regions, which are this 4 here. Sorry. So part of this 2 panel are the observational study, while in the bottom one we have the analysis from ERA 5, just for you to orient yourself. And as I was saying, the global behavior is mainly driven by the middle latitudes, while tropical regions here in blue and cyan, they have quite a different behavior. And focusing on the tropical regions, what we notice is that there is almost a constant offset between the two. The blue one is the tropical Atlantic, so Eureka, while the cyan one is the Benguela current. And both in the scaling with large-scale wind speed and in the scaling with the atmospheric instability, we observe almost a constant offset, and we believe this to be linked to the different boundary layer depths that are observed in these two regions, because the Benguela current being a Nahuelling region, it has much colder sea surface temperatures, and that is linked to the mixing to the boundary layer height. And as we saw, the boundary layer height matters in terms of defining the intensity of the coupling. For what regards ERA 5, you can clearly see the results are much more, let's say, diverse. But we found extensive nonlinearities in the ERA 5 results, and even the mid-latitudes regions that are very, very coherent from the observational data, have some large discrepancies, especially here in the instability. If you look at the behavior of these four curves that are the middle latitude regions, they're doing quite different things. And another interesting result is the one regarding the Bigila region, so this upwelling tropical region, which has a negative coupling, and this is almost unheard of, I believe. The only thing that I can think of can cause such behavior is if by increasing the mixing we encounter lower momentum air, and that would mean we have some negative wind shear, but that would be extremely consistent. So this is still an open point of investigation why this is happening. But there is something we share also with Reanalysis, where she was having similar troubles with some negative wind shear. So that's promising. Now to conclude, the R5 interpretation of the scaling of the coupling with environmental conditions is quite well matched in observations. There are some discrepancies in specific regional context for certain conditions, especially for very stable boundary layers. We have identified how for the strength of the coupling, not only the intensity of the gradient is relevant, but also the size of the SST features is an important element to take into considerations. And there are still quite a few open questions regarding the role of these length scales, but also the role of wind shear, as I was just mentioning, and of the boundary layer height, especially in tropical regions, that need further clarifications. And we would also like to look into the fluxes, because in the end, whether the fluxes are influenced by this coupling, because in the end, what we are all interested in is whether there is some upscaling effect of this coupling to larger scales. And so this is something we are planning on investigating using some WRF-CROCO simulation, so high-resolution numerical simulation in the near future. So that would be all from me, and all the content, most of the content of this presentation can be found in the paper we recently published, and you can find the title and the QR code here in the last slide if you're interested. Nothing. If you have any questions.
All right. Thank you very much, Lorenzo, for the presentation. So, as usual, whoever has a question can raise her hand or type it in the chat, and we'll read it out loud. So, I don't know if there are any questions. Please add Stefan, if you want to ask your question.
Yes, you hear me?
Yes, we do.
I have several questions. First, maybe a clarification, which I might have missed it. So you use error 5 reanalysis from the portal? Or do you use some kind of first guess? Because the one is physically more consistent than the other, I believe. So if we, because the reanalysis, of course, assimilating scatterometer data in it, and therefore is changing the surface wind field in places where there is scatterometer data, which is not everywhere. So then, depending on region, you might find a different response, because in one case the wind has been changed by scatterometer data, in the other case it's not. So that could cause some noise. To avoid this noise, you could use, in principle, the first guess, because we see that the scatterometer biases are reinstated very fast after the data estimation cycle has stopped. So that could be a difference in response. That's what I'm trying to say. The other thing is more about so we see large errors in the wind of error 5, and particularly in wind direction. Of course, you also use wind direction in principle to get your component, I guess, across the SST. So you then sort of build in the errors of error 5 perhaps into the analysis you're doing. And then the last question is maybe about whether you also looked at the effects on vorticity or shear, in fact, because if SST gradients align with the wind, you also get some effect, and that can have dynamical consequences. Did you look at that or not? So that's maybe two questions.
Okay. Yeah, we have used the R5 product from the portal, but indeed we are considering from some other analysis also to look into the first guess one. So that's something we are for sure going to consider. The second question was about the wind directionality. We haven't really focused on correcting these results, also because our goal here was to compare to the previous work of the Biol et al. And to extend it down to this regional level. So the idea was not really to focus too much on AR5 performance on that part of the analysis, but rather to look into the observations in order also to guide ourselves for further analysis using fluxes and using models that clearly provide us with much more information that is absolutely relevant for this problem. So no, we haven't corrected it, but I believe this modification is mostly relevant in the tropics, right? The error in wind direction.
It also happens at higher latitudes, so it is not strictly
Okay.
tropics. The effect is biggest in the tropics, you're right, yes.
Okay, perfect. So yeah, maybe that could be the cause of part of our uncertainties. Yeah, absolutely. And with regard the last question regarding the wind shear, we haven't investigated that, but that's on the to-do list definitely, because we clearly do expect mixing. Up to now we have been working in approximation as a like observation guys, people. We have been relying on observation at the surface, so we didn't really have a way to look into the vertical. And the first attempt that we are doing are using the WRF database the WRF simulation that I was showing you, have some interesting show some interesting effects from that point of view. And so definitely we want to look into that. We would also like to look into some specific conditions, for instance, like in downdrafts, where we have some negative wind shear, to see whether the increase in the mixing momentum with lower mixing air with lower momentum has an effect, or if there is some sort of threshold that is reached. Because I don't remember if it was during the last presentation of Louise, but no, I don't think it was in the last seminar, but there is some reasoning on what happens when we encounter some negative wind shear, if the mixing increases, or there is some discrete behavior, sort of stratification driven by this, by the wind shear. So that's something definitely we want to look into. Thank you.
Okay, thanks a lot. Yes, as you know, the error 5 first guess and the corrected first guess is available in the Copernicus Marine Service as a level 4 product from KNMI. So if you're interested, you already have the data, let's say, on the data.
Yeah. Great. Thank you.
Yeah. Thanks.
Thank you. Thanks. So please, Roger.
Oh, thank you. Thank you, Lorenzo, for a very interesting talk. And I hadn't seen an analysis of the dependence on wind speed before. I have a couple of different questions. Maybe I'll ask one of them. I guess one of them is about the joint distribution of the boundary layer height and the wind speed. And also, I may have just missed this, but how you are characterizing the horizontal scales over which you think these gradients are important in the various products. So did you look, for instance, at how the boundary layer height and the wind speed dependencies may be aligning together? In other words, do you get the same wind speed dependence regardless of boundary layer height? And do you get the same boundary layer height dependence regardless of wind speed?
Yeah. Well, clearly these refer to the study regarding the WRF data, because from observation we do not have the estimate of the boundary layer high. I think I might have in the appendix actually a recent result. Let me see. No, unfortunately, I don't have it here. But yeah, from WRF data, we are looking into this the cross correlation. Well, we are looking into the coupling intensity when we look at both the variables together, and this is, for instance, what I reported here. This is still from the observational study for air sea temperature difference, and we are looking similarly to what we are doing here at the composite contribution. So we are looking at specific conditions, both in terms of wind speed and instability. And we are estimating the coupling in these conditions. And I don't have it here, but we observe something quite similar to these results, also for what regard the boundary layer high. So by substituting basically instability with boundary layer high. And clearly there is a correlation amongst all these variables. Like in WRF, boundary layer high is obtained by looking at critical Richardson number. That depends ultimately on geostrophic wind speed, depends on buoyancy, which is linked to the air sea temperature difference. So clearly there is a dependence. And disentangling this dependence, I'm not sure is the goal here, because we are also looking at winds, but we are interested ultimately in how the fluxes work. So we are still looking for the optimal quantity to look at and their composite contribution for sure. For what regard, so we do not have those results you were asking for observation clearly. For what regard the definition of the scales where this coupling matters, we have, let me think if there's something about it. No. Well, basically the way we were identifying the fine scale were by filtering all the large scale wind variability and large scale wind variability using Gaussian filters. And for the observation, we have used a sigma of 50 kilometers. So the idea is removing all the variability for scale larger than, let's say, hundreds of kilometers in the end, which is quite compatible with all the previous results. But as I was showing you, and as we also have investigated during the Air Sea Interaction Hackathon held by the Hamburg University last year, together with Luis Nuyens, there are some, like the mechanism are also active at finer scales. So it's in terms of scale, I think there is a dependence on the scale we should look at, depending, for instance, on the latitude, how we should define the scale for the SST and wind gradients that we compute. But as I was saying, it depends on the latitude. And also, just by taking derivatives, you are applying some sort of filtering. So it matters relatively which are the scales that you remove, the large scales that you remove, and what you define as fine scale.
Okay, thank you. I had another question, but I think I should let Jack go ahead.
We can go with Jack, and then if we have time, you can ask the second question as well. Please, Jack.
Thank you. Yeah, you've partially answered it with the answer to the previous question, actually, but I was just going to ask if you can say a bit more about the boundary layer height calculation. It's coming from the model, I understand that, but the kind of the idea can be conceptually simple, but the detail often for that kind of calculation, maybe things get more fuzzy. Are you reasonably confident that it is characterizing the boundary layer height well enough to do what you want it to do?
I'm reasonably confident in the people that are providing have developed these models, but this is exactly the idea of our next steps in this research, because we are this result that I was showing you about boundary layer high is absolutely preliminary result, and like the definition, as I was saying, is obtained by through a computation of the bulk Richardson number, critical Richardson number. which is a way of defining the boundary layer height, but depending on the application that you're interested in, maybe that's not the best definition. So clearly what we are interested in, as I was saying in the first question for Ad, I believe, regarding the wind shear, we're interested really in studying the air that we are mixing, the profile that we are mixing, rather than what is the point where we reach the geostrophic wind. Like, this is clearly important, but maybe at a certain point we stop mixing far before that. So that's the idea for our next steps, is try to characterize as a sort of environmental conditions the vertical wind profile that we observe, rather than the boundary layer height.
And the thermal profile too, in the kind of, because those kind of metrics can often, I guess, be quite surface based if you're looking at things higher up too in terms of stratification. Is that maybe that's what you mean, but is that part of that calculation too, rather than just purely based on the wind?
Well, no, for sure. Like, for sure, we are going to have to take in consideration of this also, because we are interested in, ultimately, if we encounter a layer with higher buoyancy, that's going to affect the way the mixing works. So absolutely, we're going to have to consider profiles of wind, of possibly humidity. There is a recent work by I don't know, it hasn't been published yet, but there are some interesting work regarding how these couplings influence mixing from a humidity point of view, because entrainment is involved, and so that's also part of the mechanism. So yeah, definitely we're going to consider also thermal profiles.
Right, thank you.
Profiles. And congratulations for your lesson. I really enjoyed it.
Oh, thank you. Yeah, this has been a great talk, very clear, very interesting work. So thank you.
Great, thanks. I propose, Niklas, please.
Well, thanks a lot. Very interesting talk. Enjoyed it very much. I just wonder, two questions. The first, you showed that the coupling coefficients drop off at the very lowest wind speeds, and I wonder whether that could be an impression or an expression of the pressure effect, that basically the sea surface temperature imprints itself on the hydrostatic pressure. And the second question is, since you're pointing at scale dependence, why not go to wave number space?
Sorry, can you repeat the last sentence?
Since you're looking at scale dependence, why not go to wave number space?
Okay, I will answer first the first question regarding the behavior for low wind speed. Sure, at a certain point, as your paper was showing, by decreasing the Rossby number, there is a shift toward the mechanism which is more relevant. But I'm not here to tell you that clearly. We also expect, since we're using scatterometer data, that below 4 meters per second, the estimates of wind speed start to be not exactly reliable. So in our model, in the fitting here, there was this term that I haven't talked about, but this is just a bit instrumental, but this term U0, which was our estimate of when the linear behavior was converging was reaching the zero, the intensity equal to zero, which is a bit of the estimate where we expect the coupling to become negligible or stop working, either because we are not able to identify the wind direction or because the wind estimate is not reliable anymore. But as you can see, also our data stop basically at 4 meters per second, which is I think in the literature, the reference, the minimum, the bottom limit for the reliability of scatterometer estimates. So I think this is not the right framework to investigate that behavior. And yeah. Also, okay, and with regards to the second term, we have thought about adopting the spectral methodology, but our focus was to try to preserve the fine scale variability as much as possible. And as I was showing you in the beginning, what we are seeing here from the metadata is that radiometer observations of SST are not gap filled. And in most of the situations, you don't have more than like 50, hundreds of kilometers without some gaps due to cloudiness, due to dust. So it's quite complicated to look into spectral features if we don't have a gap filled product. And we didn't want to lose the fine scale information by and employ a L4 product or something like that. Yeah.
Okay, great. Thank you. Thank you very much. Very interesting talk. Thank you.
Thank you.
Thank you again. So please add if you want to ask another question.
It's maybe more like a comment.
Please.
Of course, we took a lot of trouble to validate scatterometer winds with triple collocation. You can find publications, literature about it. We don't see much evidence of lower quality low winds. But of course, there is an interpretation issue. Of course, the idea is that we look at ocean roughness with microwaves. So there have been studies done on looking at the effect of wind variability. Of course, wind variability within the scatterometer footprint will enhance the roughness and will give higher wind speeds, because that's how we interpret it. We cannot distinguish between wind variability and we just mentioned the mean of this interference of microwaves with the ocean surface. Yes, we think this only is relevant for quite low winds, about let's say below 2 meters per second. That this interpretation difficulty is important because wind variability is generally not extremely high. So with buoys we get about around 1 meter per second. So it makes sense that around 2 meters per second we start to see the effect of the wind variability in the scatterometer data. In terms of geophysical model function, the sensitivity at low wind speeds is clearly sufficient. So I don't think there's a measurement problem. There's only maybe this interpretation problem. But that's only for winds, I would say, below 2 meters per second, maybe, where you cannot be sure whether you look at the wind variability or the wind speed. So that's what I know from my work with the scatterometers.
Thanks.
Okay.
Very clear. Please, Roger. Yeah, I was coming back to you.
Okay, thank you. Can you go to the slide in which you had the little sketch of the profiles of the wind and the transition from the cold to the warm? Yes, and then in this one, you had another one in which in the cold to warm transition, you had the indication of downward mixing sort of sketched in. And, you know, I've always, except in unusual situations, had a more equilibrium-based understanding of how this works. And I really am puzzled in this downward mixing scenario. If I understand what you're saying, you're seeing it more as an inertial advective response. What happens then in the warm to cold transition? You know, if you think it's the opposite of the downward mixing, then you must have downward unmixing. You must have a sort of Maxwell demon that takes the slow-moving air and moves it towards the surface, and the fast-moving air that moves it upward, in order to get that shallower, the shallower slow layer and the farther downward extent of the fast layer. And so I've always looked at this as being driven mostly by the pressure gradient. And the question is, how far does the stress divergence get distributed that opposes that pressure gradient? So I guess that's sort of my question is, what is happening in the warm to cold transition if this is an advective process? Do you see what I'm driving at?
Yeah, absolutely. What we expect and what we kind of see also from the data is that the mechanism at play is slightly different than from the cold to warm transition. As I was showing you here, is there is a sort of restratification in the warm to cold transition, rather than so it's. Yeah, I see it personally as an effective problem in the sense that we have then the warm air masses that is affected over this boundary area stratification, and then that's linked, for instance, with the creation of clouds, but that's a bit of a different topic. But what we expect is that there is this stratification which is much quicker in terms of the influence on the surface wind than on what we have observed for the transition from cold to warm. And this is quite clear from the fact that there are slightly different mechanisms at play is quite clear if we look. And this is going to take a while now, but I hope I have the result here. Let me. Okay, if you look, for instance, here, you can clearly see there are different behaviors for different slope, and therefore a different intensity of the response for negative SST gradients. Sorry, no, this is not. Yeah, the label here is wrong. This is the SST gradient. For negative SST gradients rather than for positive ones. This is a bit of an extreme case because this is almost flat, but yeah, there are two mechanisms, slightly different mechanisms at play that I think they depends differently on the other conditions. But that's the case only in specific conditions. Most of the time, the relation is quite linear. I don't know if I answered your question.
Okay. All right. Thank you.
Anything more to
I'll try to understand that a little better. Thank you.
I don't know if Agostino has something to add.
Yeah, no, I think the argument we can bring forward is what you were mentioning, Lorenzo. So we see a different slope, and there is always a stronger response when you go from warm to cold, and this, within our interpretation, seems to agree with the fact that you can form a thinner boundary layer, so the response is very effective because you have a relatively low amount of air to influence. So, and we see this type of asymmetric response when we look at high resolution data, so a daily and kilometer scale data. So I don't know. I mean, we cannot give a definite answer, but this is what the data are showing.
Okay. So it seems as though there's a different understanding of the momentum balance then and how it operates in the transition. But I don't quite understand what your picture is, what that balance is as you go from warm to cold. So, but I think we're running out of time.
Yeah, we'll think about that more.
Great, thank you.
Thank you very much. Yes, so I think we've reached the end of today's seminar. So I thank everyone for joining, and see you soon. Next week we still have a seminar. So thanks again.
Thank you.
Thank you. Bye.
Very much.
Bye, everyone.
Thank you. Bye-bye.
Thanks. Bye-bye.